Welcome to this intro video for Module 3 of MCET 450 Advanced Mechanics. In this video, we will get an overview of the principles associated with applied stress analysis. Each module lecture starts with an example of an engineering failure that either resulted in severe injury, loss of life, or significant financial loss. As engineers, we need to be competent in our professional practice so that these issues do not occur. I am sure no one wants to be responsible for the death or injury of people because our design was faulty or lacking in some way. In this example, every one of the window panes in the John Hancock Tower in Boston had to be replaced due to poor structural integrity. Fortunately, the engineers found their error before any injuries occurred, but the expense was about $7 million. When a machine member carries load, every single point of that part responds to the load in some way. The responses include stress, strain, and deformation. Each point will respond differently and will have a different magnitude of stress, strain, or deflection. These three responses are interrelated, and as engineers, we often focus on the stress response. The most basic definition of stress is force per unit area. In some cases, stress is calculated by directly dividing the force by the area. In other cases, the computation is not as direct, but the end result still has units of force divided by area. There are four main types of stress. There is direct or normal stress, which consists of two subtypes, that's compressive and tensile stress. There is shear stress, which results from a load that effectively bisects the machine member. Bending stress results from loads that deform the part along its longitudinal axis. And torsional stress results from loads that twist the object about its longitudinal axis. Stress and pressure use the same units, and compressive stress is effectively the same as pressure in some cases. Forces result from mass and acceleration. In the SI measurement scheme, 1 kilogram times 1 meter per second squared equals one force unit called a newton. A newton is a unit of force, not stress, and it is important to keep straight when performing engineering analysis. When the term load is used in mechanics, it always means force. However, forces and loads result in stresses in the machine members. Area is a measurement of a surface, effectively the amount of flat space present. Areas have boundaries. The most basic area is that of a rectangle or square. The formula is the base times the height. In SI units, this results in meters times meters, so the base area is 1 meter squared. When a force is equally applied over an area, we get stress. So that results in newtons divided by meters squared. This should not be confused, but apparently it often is, with units of moment or torque, which are newtons times meters. So for stress, we have newtons divided by meters squared, but for moment and torque, we have newtons times meters. We need to keep these straight in our minds. The SI unit that is equivalent to newtons per meter squared is called the Pascal. To convert between newtons per meter squared and, say, newtons per millimeter squared, one must exercise caution. The conversion factor is not simply 1,000 because there's 1,000 millimeters in a meter. You must remember that the meters are being squared. Thus, the conversion unit is 1,000 times 1,000, which is 1 million. In the U.S. customary system of measurement, the pound is the standard unit of force. In the most basic system, The slug is a unit of mass, and the unit of acceleration is foot per second squared. Thus, 1 slug times 1 foot per second squared equals 1 pound. However, in the late 1800s, units of pounds mass replaced units of slugs, requiring the inclusion of a gravitational constant in any calculations converting between force and mass. In stress analysis, we are mainly concerned with forces, and thus we rarely need to make this conversion. While feet, or the foot, is the standard unit of length for the U.S. customary system, in mechanics we generally use the inch for our length measurements. This lends to the use of pounds per square inch, PSI, for stressed units. At times we may encounter pounds per square foot, but this is uncommon and will often need to be converted. The conversion factor between pounds per square inch and pounds per square foot is 144. As mentioned earlier, we must be careful not to confuse units of moment with units of stress. Also, I recommend including units in all written out calculations to allow you to use the factor label method. This method is demonstrated here on the slide. This allows you to confirm that your calculations result in the correct units, thus acting as a fail-safe against miscalculations. That's it for this video. Thanks for watching.